It is the autumn of 1943, and somewhere in the industrial heartland of occupied Europe, a night shift foreman is doing his rounds. The factory floor hums and shudders in the darkness, the air thick with the smell of hot metal and machine oil. Overhead, the great smokestack draws its breath, pulling heat from the furnaces below and exhaling it into the cold sky above the Ruhr. To the men working beneath it, that stack is as permanent as the earth itself. It has stood through bombardments, through Allied leaflet drops, through the anxious years of occupation. It is, in every practical sense, indestructible. He does not notice the two men who slipped through a gap in the perimeter fence 3 hours ago. He does not see the small device they have left wedged inside a ventilation panel near the base of the furnace housing, an object no larger than a tin of boot polish, wrapped in ordinary brown paper, indistinguishable at a glance from the dozens of maintenance packages that move through a factory every day. By the time the foreman completes his next circuit, those two men are already kilometers away, cycling through back lanes toward a safe house they have memorized from a hand-drawn map. 48 hours later, the smokestack begins to lean. This is not the story of the bombers, the Lancasters and Halifaxes that rained destruction from 30,000 feet. This is a quieter story, and in many ways a more extraordinary one. It is the story of how a small, secretive organization, working from suburban offices in Baker Street, London, developed a range of incendiary and destructive devices, so precisely engineered, so cunningly disguised, and so devastatingly effective that they could bring industrial production to a halt without a single aircraft crossing enemy airspace. These were the sabotage weapons of the Special Operations Executive, the SOE, and for decades after the war, much of what they achieved remained locked in classified files, acknowledged only in whispers by the men and women who had risked everything to use them. To understand why these devices existed at all, you must understand the problem that confronted Britain in the early years of the war. By the summer of 1940, Germany's industrial base was running at extraordinary capacity. The great factory complexes of the Ruhr, of Silesia, of the Rhine Valley, plants manufacturing aircraft engines, ball bearings, synthetic rubber, armor plate, artillery shells, were producing at a rate that Allied planners found deeply alarming. Conventional bombing was the obvious answer, but it was proving deeply imperfect. Early RAF raids suffered catastrophic losses to German night fighters and flak. Even when bombers did reach their targets, the accuracy of high-altitude bombing in the early war years was, to put it charitably, inconsistent. A study conducted in August 1941 by the government statistician David Butt concluded that only about 1 in 3 aircraft that claimed to have attacked a target had actually dropped its bombs within 8 kilometers of it. For precision targets, transformer stations, bearing plants, chemical works, that was essentially useless. The problem, then, was not a lack of intent. Britain desperately wanted to destroy German industrial capacity. The problem was delivery. High explosives carried in aeroplanes and dropped from altitude were blunt instruments. A transformer station might require hundreds of sorties to destroy from the air, at the cost of dozens of aircraft and their crews. But that same transformer, approached on the ground by a single trained agent carrying the right device, could be rendered useless in 30 seconds. The mathematics were almost obscenely compelling. This was the insight that drove the creation of the SOE's Technical Directorate, and more specifically, the extraordinary workshops that operated under the designation Station 9, a requisitioned country house called the Frythe, near Welwyn in Hertfordshire. From the outside, the Frythe looked like dozens of other commandeered country estates. Barbed wire at the perimeter, uniformed sentries, the occasional lorry moving supplies in and out. Inside, it was something else entirely. It was staffed by chemists, mechanical engineers, metallurgists, and former industrial designers. Men who had spent their careers making things work, and who were now quietly dedicated to making specific things fail. Their brief, as one internal memorandum put it, was to produce devices that were operable by a person of no special technical skill, capable of being carried without arousing suspicion, and reliable in effect beyond reasonable doubt. What emerged from the Fryth over the course of the war was a catalogue of destruction that reads, even today, with a certain dark ingenuity. But among all the devices developed there, it is the incendiary family, and particularly those variants engineered specifically to destroy industrial heating and exhaust systems, that deserve closer examination because they demonstrate most vividly how precision sabotage could achieve what bombing could not. The core challenge with attacking an industrial smokestack or furnace system was this. You could not simply place an explosive charge against the outside of the structure and expect useful results. A smokestack built to handle temperatures exceeding 600 degrees Celsius and designed to withstand the thermal expansion of continuous industrial use was, structurally, enormously robust. Conventional explosive damage to the exterior would be repaired within days. What was needed was something that attacked the stack from within. Something that exploited the very conditions that made the structure seem so permanent. The solution the engineers at Station 9 developed centered on a principle of thermally induced structural failure. A smokestack, for all its apparent solidity, depends on uniform heat distribution through its lining. The internal brickwork, typically a high-grade refractory material capable of withstanding enormous temperatures, expands and contracts in a controlled, predictable pattern as the furnace cycles through its operating temperatures. Disrupt that uniformity, create a localized hotspot of sufficient intensity at the wrong point in the lining, and you could induce cracking, spalling, and ultimately the catastrophic structural failure that would bring the entire column down. The incendiary devices developed for this purpose were remarkable in their compactness. A typical specimen measured roughly 15 centimeters in length and no more than 5 centimeters in diameter. Small enough to be concealed in a standard tool bag or even a coat pocket. The outer casing was designed to look at casual inspection like a piece of standard industrial hardware. A pipe fitting, a maintenance canister, an electrical junction block. The disguise was not merely cosmetic. The devices were tested extensively to ensure they could pass scrutiny from a factory foreman or a suspicious guard without raising alarm. Internally, the device contained a two-component incendiary compound, separated by a thin partition that would dissolve when exposed to moisture or, in some variants, when a simple time-delay acid fuse burnt through. Once the partition failed, the compounds combined to produce a sustained thermite-based reaction capable of reaching temperatures above 2,000 degrees Celsius, roughly 4 times the operating temperatures of the furnace lining it was designed to destroy. At that temperature, the refractory brickwork did not merely crack, it liquefied. The manufacturing of these devices was divided across several facilities to protect against the compromise of the entire program. Final assembly took place at the Fryth and at a secondary facility operated undercover near Aston Clinton in Buckinghamshire. Components were produced separately at subcontracted workshops, whose owners were told only that they were making precision parts for specialist industrial testing equipment. Exact production numbers remain classified, but internal SOE correspondence from 1943 suggests that several thousand units of various incendiary types were produced and dispatched to occupied territories during the peak years of the program. Delivery of these devices into Germany and occupied Europe was the work of the SOE's country sections, operating through networks of agents, couriers, and resistance groups that stretched from Norway to Greece. The incendiary devices intended for industrial targets were typically carried by agents who had been given cover identities as maintenance workers, electrical contractors, or traveling salesmen, occupations that gave them a plausible reason to be carrying tool bags into industrial premises. The actual placement of the device could, in ideal conditions, be accomplished in under a minute. An agent with access to a maintenance corridor running adjacent to a furnace room needed only to locate the ventilation panel or service access point identified in their briefing materials, wedge the device in position, and leave. The time delay fuse, adjustable between 12 hours and 72 hours depending on the variant used, ensured that the agent would be well clear before anything happened. Operational records where they survive. Operational records where they survive point to a number of confirmed uses across German and German-controlled industrial facilities. The synthetic rubber plant at Huls in the Ruhr suffered a furnace failure in the spring of 1943 that production engineers at the time attributed to a fault in the refractory lining. Post-war analysis of surviving SOE records suggests the failure was almost certainly induced. Similar incidents were recorded at electrical transformer facilities in Belgium, at a ball-bearing plant in northern France, and, in one of the program's most significant operations, at a steel works in the Protectorate of Bohemia and Moravia, where the collapse of a structural chimney halted production for an estimated 11 weeks. If you are finding this interesting, a quick subscribe helps more than you know. The psychological dimension of these attacks deserves particular attention because it was, in many respects, as important as the material damage. A bombing raid, however destructive, was externally caused. The factory workers and their managers understood what had happened and could begin immediately to plan repairs and resumption of production. An internal failure was something altogether more unsettling. When a smokestack began to lean, when a furnace lining cracked for no apparent reason, when production halted and no saboteur could be found, the effect on factory management was corrosive. The Gestapo would be called. Workers would be questioned. Trust broke down. Informers proliferated. And all of that internal friction, the suspicion, the investigations, the security reviews, consumed management time and energy that would otherwise have been directed at production. The Germans were not, of course, unaware that such attacks were taking place, and they were not without their own responses. By 1943, German industrial security had been substantially tightened, with factory premises subjected to regular searches and all maintenance work requiring documented authorization. The Abwehr, German military intelligence, had compiled assessments of Allied sabotage capabilities and circulated guidance to industrial managers on the types of devices they should look for. These assessments were, in several particulars, wrong. The Germans expected SOE devices to be crude and easily spotted. The actual devices from Station 9 were far more sophisticated than German intelligence appreciated, and their disguise as ordinary industrial components repeatedly defeated searches that were looking for something that looked like a weapon. For comparison, the German equivalent program, Amt 6 of the SS Security Service, produced sabotage devices that were technically competent but considerably less refined in their disguise. German operatives did deploy incendiary devices into Allied territory, and a small number of industrial incidents in Britain and the United States during the war may have been German sabotage rather than accidents, but the overall scale and effectiveness of German industrial sabotage against Allied targets was, by most assessments, substantially inferior to the SOE program operating in the other direction. The Americans, through the Office of Strategic Services, developed their own range of devices in parallel with the British effort. Many of these were directly influenced by SOE designs, and there was a formal program of technical exchange between the two organizations from late 1942 onwards. American devices tended to be somewhat larger and, in some instances, more powerful than their British counterparts, reflecting a slightly different doctrine that emphasized maximum destruction over subtlety. The SOE philosophy, by contrast, consistently prioritized deniability and resistance to detection, on the pragmatic grounds that an agent who avoided arrest was worth a great deal more than a single spectacular device. The actual impact of the SOE's industrial sabotage program on German war production is, even now, difficult to quantify with precision. German production records for the period are incomplete, and the disruptions caused by sabotage are not always distinguishable from those caused by Allied bombing, equipment failure, or raw material shortages. What the post-war United States Strategic Bombing Survey noted, with some grudging acknowledgement, was that in certain key sectors, precision bearings, synthetic fuel, optical equipment, disruptions to production appeared to be disproportionate to the bomb damage visible at those facilities. The implication, which the survey did not press too hard, was that a proportion of those disruptions had been caused by means other than bombing. Perhaps the most lasting legacy of the SOE's incendiary program is not the damage it caused, but the principles it established. The idea that industrial infrastructure could be attacked not through destruction from without, but through precision interference from within. Disrupting T.